Hey, Professor Cam. It's Jordan, just wanting to answer those questions for the oral exam. So here we go. So for the first question, describe what's been the hardest topic to understand this semester and why it's been so hard. So this isn't my first time taking a calculus course, but what I found normally that I have the most trouble with um, is if I have to pick one thing, it would probably be related rates, just because um, I have a real tendency to overcomplicate things. And so it takes me a while. I really have to force myself to slow down and to think about really what the question is asking and what I'm supposed to be finding. Because a lot of times I'll just fly through it and then I'll be at the end just asking myself, what's going on. So a lot of times for me, it's just a matter of slowing myself down and realizing, okay, this is what I have, this is the information I've been given, and then this is how I need to put these things together in order to find what I'm looking for. And I find that when I do slow myself down, it becomes really, really easy and just a simple, machine that I can start walking through. So that's probably been the hardest topic so far this semester, just because of not necessarily my lack of comprehension, just because of my own flaws and wanting to run through things too quickly. So for the second question, um, for putting myself in the role of the instructor, describe how I explain implicit differentiation, what it is, when, and how one uses it. So, to me, implicit differentiation is really useful when you have a function that would be really hard on its own to take the derivative of, or if all of the terms are jumbled together, if it's not in standard form, if it's something that, I guess for lack of better terms, just looks more meaty than you're used to, or if it looks like you something that can't tackle. Implicit differentiation is a really good tool to have in your toolbox to be able to not necessarily worry about separating and isolating y as a getting everything in term y in terms of a function of x, but more so just leaving the function kind of as is, and then being able to still take the derivative of it to get a useful application, whether it's on a graph or some sort of data analysis. I think it's really useful when you're looking at like graphs of curves that may not even look like a function on their own, but when you're looking at just one portion of the curve, like the circle example that we did in class, it can be really useful to think of that as just part of the graph. And so you can look at part of that curve, like the top of the circle, or just like the bottom part of the circle, and use implicit differentiation so that you can use just a coordinate rather than one value, one input. You can use two inputs to kind of isolate that portion of the graph that you're talking about and still be able to get a meaningful derivative that you can still interpret in a pretty good sense. So I guess to just kind of recap that, implicit differentiation, really useful when you have a large function, a meaty function that you don't really know how to isolate, that you can't really wrap your head around, maybe factoring to one side, or maybe it's just something that is not a function in general, like the equation of a circle, or some other case where you have some kind of curvature where you need to find the slope of the line. You need to take that derivative to find the slope of the line, but you can't isolate the terms that you need to get it into that standard form, that more generic form that we're used to. And so just being able to take that and then differentiate implicitly with respect to y and x individually, while using the chain rule within it to make sure that everything is accounted for. This is probably an important thing to mention. Just when you are doing implicit differentiation, I feel like I'm talking as the instructor, so I have to include this. But just being able to realize that when you're differentiating the terms, the x and y terms, you have to make sure that x is being differentiated in respect to x. So there's nothing you really have to do there. It's just a normal derivative. But when taking the derivative of a function y, you do have to treat that as a function rather than a variable. And so because you're differentiating y in respect to x in just the generic form with y's and x's in there, it's important to also multiply, to do the chain rule, to multiply your y function by y prime. And so to make sure you include the chain rule in there, because it can be kind of tricky, and it took me a while to get it at first. But once you wrap your head around it, it does make sense, and you can start flying through it a little better. So that's implicit differentiation. So for the third problem, or the third question really, so besides the question that we're going to talk about in the next answer, so for 4, you want me to pick one problem on the WEDWork exam that I don't feel that I got correct, explain why I didn't feel confident in my response, and where I would go about solving it now. So I don't really think that there was anything on the exam that I didn't know how to tackle. I think my worst enemy on the exam was time, because I tend to be one who goes back and is really methodical, who checks his work. And before I left a question, I wanted to make sure that I had my insanely long explanation written out. I'm sorry in advance for when you're grading it. My explanations are really long, especially in the first few problems, because I really wanted to take my time to make sure you understood how I was thinking about it. But probably if I had to pick one problem, it would have been, for me at least, 6 or 7. At the end of the exam, it was that question on implicit differentiation, and we basically had to implicitly differentiate this this equation, and the right side was really easy. It was just like 2x times 2y prime, something along those lines. But I ended up not having a lot of time at the end of the exam, so I was rushing through it just to at least get an answer down. And I ended up being able to do it just really quick, scratching on the paper, but I don't know that I was able to get the finer answer. And I think I just said that I didn't have enough time to finish or something like that. But in the description, I did go and I explained how I would have solved that problem if I had more time. So I guess to answer what I would have done in the exam and how I would go back to do it now, I mean, it's kind of the same thing that I explained in the last problem. So with the implicit differentiation, you're just differentiating in respect to x for both terms. So in the x case, it's totally normal derivative, but in y's case, it's a function of x, so you do have to use the chain rule. So I know on the left it would have been, I think it was 2 parentheses x plus y, it was something along those lines, or x squared plus y squared. I think it was x squared plus y squared. But you would implicitly differentiate that, so you would have something like 2x on the first term. The second term would be something like 2y prime, and then on the right side there was this weird, it was almost like a cubic term, and so you ended up having to go through and factor it out, and what you ended up with when you take the derivative is this FOILed term. It's 2 trinomials that you have to FOIL out, and that's where I was running into a problem with my time, is FOILing each of those terms individually before being able to get an equation that I could put in standard form to plug, or even just an equation in general that I could plug my x and y coordinate into to get that answer. And so if I had more time, I would definitely be more methodical about that in thinking through the steps. But I feel as though the arithmetic that I at least had time to do on the scratch paper, that as I was working through the problem, that was on the right track. So that's what I would have done. If I could have gone back to redo the exam, I just would have not taken as much time in the explanations and trust the answers that I was getting, because to an extent I feel like it did come back to bite me in the butt, because I was taking a really long time explaining my methodology, when in some cases I think that you could kind of infer that I had to make some conclusions and in my calculations, or you could kind of infer how I got from one place to another. So I would probably just be less explicit on my explanations, because they were like a paragraph long each, and instead I would have taken a lot more time on the arithmetic of it to make sure I had the correct answers. All right, so for question 4, you probably feel like you've been here an hour by now, so I'll try and wrap it up. But this is basically talking about for me, it was the first question on the exam. It was the exam question where I was given 3 graphs, all on the same coordinate plane, and asked to identify which was the original function, the derivative, and the second derivative. And you basically want to know how I went about determining the answer, making sure that I address my response, and how I approach determining each one of the functions individually. So I obviously, and I wrote all this out in my description on the exam, but a lot of it was done with just picking like single points on the graphs, whether it be at the origin or like at x equals 3, and just comparing where the graphs were at and what I knew to be true about the characteristics of graphs and their derivatives and their second derivatives. And so I had to rely a lot on just the relationships that we've talked about in class. So stuff like the first and second derivative tests, realizing that anytime the slope of the regular graph was 0, that the derivative graph wouldn't level out, but it would intersect that x-axis. It would touch it at some point, whether it's going through or just curving and kind of just touching it and coming back up. I knew that any time that on my original function I had a slope where it was 0, whether at the top of a maximum or at the bottom, kind of at that minimum point, anytime that derivative, that tangent line was 0, I knew my first derivative graph had to cross or touch that x-axis somewhere. And kind of along the same lines of that, I knew that anytime there was a point of inflection where the derivative would stop increasing and start decreasing, so if you're coming up the side kind of that curve, anywhere like along these points here where that derivative keeps going up, keeps going up, keeps going up, that point of inflection here where that derivative then starts coming back down, you know that that's going to be a 0 point on the second derivative. And so you know there's going to be some kind of crossing of the x-axis or touching on the graph of the second derivative. And a way I kind of checked my sanity on that one was essentially doing the same thing I did for the first derivative test, but instead of looking at the original function in the first derivative, I took the first derivative graph and I treated that as basically as my original function. And once I kind of had an idea in my head, okay, this is the original function, and I think that this is the derivative because at each one of these points it matches up, you know, I was then able to kind of check that, make that sanity check between the first derivative and the second derivative, and that anytime that the first derivative had a slope, a tangent slope that equaled 0, I knew that the second derivative had to also touch or cross the x-axis. So it's a similar logic that I employed, doing things like just the sign diagrams in my head, picking a point and saying, okay, this is the original function. One of the things that I think tipped me off, and I think is important to mention, is what was going on around the origin, because it was kind of funky looking. Basically, you had one of the graphs kind of plateaued and was up near like y equals 1, something like that, and it plateaued kind of above origin. And then you had the other two graphs kind of dip down, and both of them went through origin at 0, 0. So I knew that there was something weird going on there. And it's something that I don't know if I've necessarily seen it before or if it was just kind of an intuition. But it made me, my first instinct was to check out the graph that wasn't crossing through origin. So I immediately went up to the one that was kind of plateauing around y equals 1. And I just kind of did a sanity check with that. I know in one of our online office hours you had talked about one of the only cases of the first and second derivative, those could be 0, but it was hard to find a relationship between them unless you had something that was like extra super flat when it crossed that 0 point. And so it was kind of cool seeing that in the exam. When I singled out the one graph that wasn't crossing the origin, I realized, okay, hey, that has a slope of 0, it looks like, right at the origin. So I know that the first derivative has to be crossing or touching 0 at the origin right there. And conversely, I knew that one of those graphs, whichever they were, that were touching the origin, if that was at 0 and they were both crossing through it flat, so I knew that one of them was at least the first derivative, one of them was the second derivative. And so that kind of secured in the logic that the graph not in the origin was definitely my main function f, and that the other two were f prime and f double prime. And so that was kind of a good sanity check. And then just making sure that At the other points, once I knew what my original function was, just doing the things like I said with the first derivative test, the second derivative test. Another big thing that helped was concavity with the second derivative test. Looking at how the parabolic shapes opened, whether up or down, helping to determine what slope that second derivative should have, whether it should be positive and keep going positive, or positive to negative, negative to positive. Those were all things that I used in kind of deducing which was which. And eventually it came down to, once I found out what my first function was, I found out where all the zeros were, and there was only one real graph that corresponded to that, where it crossed the x-axis every time. I knew that was my second derivative, and then just as a sanity check, I went through and made sure that all of the 0 points on my second derivative corresponded with inflection points on the first graph, and so forth and so on. So I think that if you could interpret any of that jumble together, there were a couple key things that helped in my differentiation of those two things. So I hope I answered all the questions. I know it's been kind of crazy here lately with everything going on. Quarantine is definitely interesting, but I definitely appreciate your flexibility and being able to really just help us go through everything. And geez, I'm already at 16 and a half minutes, so I am sorry that you had to sit through this whole thing. But thank you for doing that. Thank you for that sacrifice. Thank you for all the adjustments that you've made. And I hope to see you soon. So thanks.